So question 3, I can see it's a polygon, so it's probably going to be a polygon question, so we might want to remind ourselves about the rules for polygons. N minus 2 times 180 is the sum of all the interior angles, and 360 degrees is the sum of all the exterior angles. Diagram's not to scale. We're asked to find the size of angle x. If we begin by counting the number of sides on the polygon, so we've got 1, 2, 3, 4, 5, 6. It's a hexagon with 6 sides. It's not regular. All the angles are not the same, and all the sides are clearly not the same size either, so it's not a regular one. If we start with finding the sum of the interior angles, equals 6 minus 2 times 180. So on the calculator it gives 720. And that's using n minus 2 times 180, sum of interior angles of a polygon. If we subtract the 110 and the 90 away from 720, minus 90 minus 110 gives me a total of 520, and then 520 divided by, we've got 3 and 3 is 6, 7, 8, 9, 10, 10x altogether. So if we divide that by 10, we'll get 52 degrees. X equals 52 degrees. Part B. Find the size of W. Once again, not drawn to scale. Give geometric reasons for your answer. So I can see the arrowhead in there. This angle W is going to be twice angle ABC. We need to find angle ABC first. Looking at this shape with 4 sides, I can see that that's a cyclic quadrilateral. All 4 corners of the quadrilateral are on the circumference. This one in here is not a cyclic quadrilateral because this vertex is not on the circumference. You have to have all 4 vertices on the circumference for it to be a cyclic quadrilateral. So in a cyclic quadrilateral, opposite angles add up to 180. 160 plus 20 would be 180. So angle ABC, is going to equal 20 degrees, and that's because opposite angles in a cyclic quad sum 180. And then we can use our arrowhead rule that says that the angle at the centre is twice angle at the circumference subtended by the same arc, or off the same arc. So angle AEC, which is W, is going to equal 40 degrees, and that's because the angle at the centre is twice angle at the circumference off the same arc. Right, next question has another polygon. So remembering our polygon rules, we might just make it a bit smaller. Get it all in. Right, now I'm going to have to work around the outside here, but obviously you would be working down below. It's a regular pentagon enclosed in a circle. We're told the radius of the circle is 5 centimetres, so if we look for all the radiuses, there's one here, 5 centimetres, and there's another 5 centimetres all the way around. Radiuses of 5 centimetres. asked to calculate the area of the pentagon. Obviously there are 5 triangles, so if we found the area of one triangle, and we're reminded that the area of a triangle is half the base times the height, then we could just times our answer by 5. So let's begin with this triangle here. Now to find the area, we need to find the base, and we need to find the height of the triangle. We're going to probably need an angle. We can't use Pythagoras because there's no 90-degree right angles, but we do need an angle. The easiest one would be to go up the top here. We've got 5 equal angles around a point. So 360 divided by 5 is 72 for this angle in here. We'd call that DOC. So you'll be writing down below, but angle DOC equals 72 degrees. Angles at a point, sum 360. And obviously we just want this half here, and half of 72 is 36 because now I have a right angle triangle. So we'll give this down here a name. It's DE, we're up to F. So angle COF is 36. Because it's isosceles triangle, I know that I can just half the angle. Perhaps we'll mention that as well. Angle COF equals 36 degrees since COD, since triangle COD is isosceles. That's why we can just halve it. Right, now we need to find this length and this length. Let's start with the height. We'll call that x. Using this angle here, I've got the hypotenuse, and this would be the adjacent side, so we'd need to use cos. So taking our time, using the triangles if you need to. Adjacent side is x, the hypotenuse is 5, and we're using the cos of 36. So x equals 5 times cos 36, 4.0450, and there's more to come. So as many digits as you can because we haven't finished the problem. Right, so that's the height of the triangle. Now if we do the base, which would be C to F, so if we call that y, and use another triangle, that'll be the opposite side now of course, because it's opposite the 36 degrees, so this becomes opposite. We'll use the SO ratio. We've got the 5 for the hypotenuse, the opposite is y, and we want the sine of 36 degrees. So y equals sine of 36 times 5, which is 2.93892. And you should probably check those. Reading off the answers. And look right. Okay, so now we could find the area of this whole triangle. The area is half the base. Well, y is actually half the base, isn't it? From here to here, this line is half the base times the height. So it's just going to be x and y multiplied together. So if we talk about the area of triangle COD, it's going to equal x times y, because this base has been halved. If we multiply those two together, .882, and there might be some more digits after that. So that's the area of one triangle. So we just need to times that by 5. So area of pentagon is 5 times, and working that out on the calculator, 59. I'm doing some rounding with it, 59.4 centimetres squared. That's rounded to 1 decimal place. So obviously you would set it out clearer down below. And the last question. Right, there's lots of information up here we need to read and put on our diagram. AF is the diameter, yes, I can see that. O is the centre. Chord EG is perpendicular to AF. So there's some right angles around here if it's perpendicular. Lots of right angles. HI is a tangent. Now a tangent meets a radius at 90 degrees, so I can tell that is true. HIO, angle OIH equals 90 degrees because a radius meets a tangent at 90 degrees. Right, FI intersects EH at K. Okay, I can see that. We're asked to prove that HI equals HK. So we're asked to prove that this length here, perhaps if I highlight it, is the same as that length there. One of the easiest ways to prove that two lengths are the same is to prove that the triangle is isosceles, because if it's isosceles with the base angles here and here, then that would be enough to show that those two lines are the same size. Right, so looking around for triangles, and in particular radiuses, so I can see that that's a radius and that's a radius, which makes this triangle in here isosceles. So let's begin by calling this angle in here a little x, which would make this angle in here a little x. I could work out that one in there, because there's a very small triangle in here whose three angles add to 180. Minus 90 for the right angle means these two add to 90, so this angle in here would be 90 minus x, and because this one here is vertically opposite it, this angle would be 90 minus x. We have a right angle here, so it's 90 degrees. This much of it is x, so this bit in here must be 90 minus x as well. And now we've proved both those angles are the same, which means these two sides are the same. That's enough to prove it's either isosceles or equilateral, and either way both those sides will be the same. So now we have to step out what we did. So we said let angle OIK equal x, and therefore angle OFK equaled x, because base angles in an isos triangle are equal. So we've justified that one being x. We need to say that angle KJF is 90. That was because of the perpendicular statement. And now we can give an angle for this one, which is FKJ. FKJ equals 90 minus x, and that's angles in a triangle. Sum 180. Vertically opposite, so angle IKH is going to equal 90 minus x as well, and that's vertically opposite angles equal. That one there. Now if we go back up here, we've proved that that's 90. We know that that's x. Angle KIH is also 90 minus x. That's just using some algebra. Therefore, since angle IKH equals angle KIH, since that equals that, then HI equals HK because base angles in an isosceles triangle are equal, and that's what we've been asked to prove. And of course there are many other ways to do it too.